Assalamualaikum and good day everyone. Today we will continue our discussion with chapter 7, which is power factor improvement. As you can see in this chapter, there are 7 subtopics that will be covered, beginning with 7.1, which is the introduction, causes of low power factor and effect of low power factor in 7.2 and 7.3, power factor improvement and power factor improvement equipment in 7.4 and subtopic 7.5. The following subtopic, which is subtopic 7.6 and 7.7, we will discuss the calculation of power factor correction and the importance of power factor improvement respectively. Okay, let's begin with the introduction. So, what is power factor? By definition, it is the cosine angle between voltage and current in an AC circuit, or in other words, the power factor can also be defined by the cosine of the load angle. The lagging power factor is produced in an inductive circuit, while the leading power factor is corresponding to a capacitive load. A unity power factor occurs when the current and voltage are in phase, or as if the circuit is holding a purely resistive load. Looking at the bottom of the page is the power triangle for lagging power factor and leading power factor respectively. In both triangle, theta is representing the power factor angle. Looking at the power triangle, OA represents the active power or the real power in watts. Vector AB represents the reactive power, where the apparent power S is represented by vector OB. The power factor can be simply defined or derived by dividing the active power to the apparent power itself, P divided to S. So we can calculate cos theta by dividing P to S. What about power factor angle? So we just find the cosine inverse of phi. So the answer will give you the power factor angle, or it is simply the angle between apparent power vector and also the real power or the active power vector. The following subtopic will summarize the causes of low power factor. Well, basically, the low lagging power factor conditions can be caused by various combination of inductive devices, such as we have induction motors, inductive load of fluorescent ballast, rectifier providing a DC power supply, arc welders, solenoids, induction heater, lifting magnet, transformers, and so on. Apart from that, the variation of load that results from socio-economic activities throughout the day itself thus contributes to the power factor value. Such activities will cause the power system load to vary, either being high during morning and evening and low at the other time. Such variation will result in the decreased power factor. There are several impacts when the power factor is low. The first one is we have to need a large kVA rating of equipment. As we know, the electrical machinery such as alternator, switchgear and transformer, they are always being rated in kVA. It is clear that kVA rating of the equipment is inversely proportional to the power factor. The smaller the power factor, the larger is the kVA rating. Therefore, at low power factor, the kVA rating of the equipment has to be made more, making the equipment larger and expensive. Second one, by having a low power factor, the system demands a greater conductor size in order to carry more current and transmitting a fixed amount of power at a constant voltage. Next, by having a low power factor, it will also result in a larger copper losses, which has commonly said as the I2R losses. And therefore, when we have a large copper losses, indirectly we have a poor efficiency system. Apart from that, system with poor power factor will also possess poor voltage regulation. In such condition, the change of the output voltage is high and results in the decreased voltage available at the supply end, thus impairing the performance of the utilization devices. By having a low power factor also will reduce the handling capacity of a system. The handling capacity of all elements within the system will automatically reduce and work below installed capacity. By considering the drawback of having poor power factor and to ensure that the system fully utilizes the installed capacity, power factor improvement shall be introduced in the network itself. In general, most of power loads are inductive, or in other words, it will consume lagging current. The equivalent model for such network is as given by the RA load in figure 1. So we have a resistor that is in series with an inductor. The power factor of the load can be increased by adding a capacitor in parallel with the load. So as if we are adding another branches with the capacitor in parallel with the existing load. This will result in a bigger power factor angle and bigger power factor value but lower power factor angle. Figure 3 depicts the angle phi 1, which is the initial power factor angle, and phi 2 as the new power factor angle after we install the capacitor in parallel with the load. It is clearly shown that by improving the power factor, the magnitude of the current drawn by the system, which is I prime, is reduced as well. Consequently, by having capacitor in parallel with the load, we reduce the losses and improve the system performance in efficiency and also its voltage regulation. The following subtopic will list out and explain the equipment required to improve the power factor of a system. Okay, the power factor improvement equipment are basically involve reactive power compensation devices. Static capacitor and synchronous condenser are the two equipment that were being used widely to improve the power factor itself. So what is static capacitor? As you can see from the figure, the static capacitor improves the power factor of the load by drawing a leading current and cancel the lagging reactive current component produced by the load itself. So such application involves static capacitor either in star or in delta connection. So we add either star or delta configuration capacitor in parallel with any three-phase load, lagging load. So by doing so, we can improve the power factor of the system. However, despite having several advantages, static capacitor has a short lifespan and easily damaged by the over voltage. The second power factor improvement equipment is the synchronous condenser, which is in fact an overexcited synchronous motor that is running at no load. By adding overexcited three-phase synchronous motor that we have like a capacitor in parallel with three-phase load, this is the synchronous motor and this is the three-phase load. The three-phase synchronous motor will act like a capacitor with the three-phase load, and the lagging reactive current component produced by the load can be cancelled out by the leading current, this over here, the vector over here, we drag over here, the leading current by the synchronous condenser. So this one will be cancelled out by this one. So this is the new current after the power factor correction, which is current I. As you can see here, the power factor angle is reduced from phi 2 to phi 1, and the power factor itself become better. So we have a higher value of power factor. The following page lists down the advantages and disadvantages of having a synchronous condenser as the power factor improvement equipment. As we can see, noise, losses, and various extra costs are the main drawbacks of the system having synchronous condenser as the equipment of power factor correction. Let's move on to some examples of power factor improvement calculation. Figure 1 and Figure 2 of the corresponding page shows the equivalent circuit and phasor diagram of power factor correction. Having V as the terminal voltage, the new current after power factor improvement is the resultant current from the parallel branches. So current that flows into the load plus current that flows into the capacitor will result in the new current I prime, which having a lower magnitude and better power factor angle. Example 7.1. An alternator is applying a load of 300 kW at power factor of 0.6 lagging. If the power factor is raised to unity, which is 1, how many more kilowatt can alternator supply for the same kVA loading. So according to the question, we have to calculate the new real power P in kilowatt after power factor is improved from 0.6 to 1, or to unity power factor. First of all, what you have to do is you have to calculate the existing kVA, which is by dividing the real power P to the power factor, the old power factor. By doing so, the existing kVA of the alternator is equals to 500 kVA. So in order to calculate the real power at unity power factor, so we just multiply S with power factor, which is 1. So we will get the real power P at unity power factor is equals to 500 kilowatt. So as we can see, by improving the power factor to from 0.6 to 1, we managed to increase the power supplied by the alternator by 200 kilowatt. Okay, next, in example 7.2, a single phase motor connected to 400 volt 50 Hz supply takes 31.7 ampere at a power factor of 0.7 lagging. Calculate the capacitance required in parallel with the motor to raise the power factor to 0.9 lagging. So the supply voltage of the system is 400 volt with 50 Hz frequency. The voltage is supplying a motor which draw 31.7 ampere at 0.7 power factor lagging. Initially the capacitor is not exist, so we add capacitor in order to improve the power factor. By having a capacitor in parallel with the load, which is the motor, the system managed to improve the power factor from 0.7 to 0.9 lagging. So as you can see from the phasor diagram, IM, vector O, IM represent the motor current, vector I represent the new load current, which is after power factor improvement. IC is the current draw by the capacitor branch. Basically, we can solve this problem in 6 simple steps involving vectors operation. So the first one is we have to calculate the active component of IM, which is over here, the horizontal component of the motor current, which is IX. And then at the same time, we know that the active component of the new current is equals to the active component of the motor. So knowing that those values are equal, we can calculate the magnitude of phasor OI, which is the new current after power factor improvement. Later, we calculate the reactive component of the motor current, which is over here, IY. Level in rate, and from there we have to calculate the reactive component of I. We can use theorem Pythagoras in order to calculate the reactive component of I. In step 5, capacitor current is calculated by deducting the reactive component of the new current from the reactive component of motor current. So you have to deduct IY prime from IY, which results 11.86 ampere. So this is the capacitor current. In the final steps, the capacitor value is calculated by rearranging the equation used to calculate the current flows into the capacitor, bringing C to the right hand side of the equation and substituting the corresponding value of capacitor current, voltage and frequency in the equation. The capacitor value found calculated is 94.38 microfarad. Therefore, it can be concluded that by inserting a capacitor with 94.38 microfarad values in parallel with the motor, the system will have a better power factor, which is 0.9 lagging instead of 0.7 lagging. As a conclusion, power factor will benefit consumer and generating stations accordingly. By having a good power factor, consumers spend less on their utility bills and at the same time increases the earning capacity of the generating station. With that, I conclude chapter 7. Till we meet again in the next chapter. Assalamualaikum and good day.